All right, so let's go and get started. Let me sort of find where we left off on our slides. I know we're a little bit further down here. Let's see. This actually might be a good place to just sort of recap where we left off. Okay, so let me go and get the sign-in sheet started. Let's see, so last time in terms of lecture, what we did is we reviewed our sort of first component, if you will, of the finite element method, which is this idea that energy principles should be applied. Energy going in has to equal energy going out in some fashion or another. We can use energy principles for basic problems like those involving linear structural mechanics, which is what we've been doing up until now. But we can also apply it for more complex stuff like what we might see later with vibration and things like that. Now, that's not the whole story, though, because we also have to consider shape functions. And I want to talk a little bit more about that so that we understand. So if we recall, again, I think by now we've beaten this into the ground, the whole process behind matrix analysis and how we analyze structures with this type of procedure. And again, the main difference with finite elements is how we actually get the stiffness matrix and how we actually get the load vectors. And that's where these shape functions come into play. And the idea is it's really little more than just a means of interpolation. It's why a lot of times they're referred to as interpolation functions and not shape functions. Either one's fine. I don't really have a preference as to which one you call it. Now, this also brought up the notion that with finite elements, which is theoretically a more approximate type of analysis than the direct approach we've been using up until now, it's not the exact answer. The more elements you use, the better your answer is going to be, but the more elements you use, the more complex your model becomes. So there's always that tightrope. Again, we're not mathematicians, we're engineers, okay? We need the close enough answer, okay? Now, finite elements will get you really close, and that's why it's so powerful, okay? Now, we looked at a bar element, and we said, well, all right, this is a pretty simple procedure. This bar element's pretty straightforward, okay? Now, this was our stiffness matrix that we derived, again, using the direct approach. We took that bar and we yanked on it, and we recorded its response. That was our stiffness matrix. I'm going to show you a more approximate approach, or a more, that's probably an incorrect way of putting it. I'm going to show you a more generalized procedure to get this stiffness matrix. Now, what's going to happen is, for this bar, we are going to get the same answer. But for more complex elements, we can apply the same procedure. And we'll get a little bit more of an approximate answer for some of those complex elements. But in the end, the process works. So it starts off by determining what our shape functions are, and that comes from assuming that this beam displaces linearly. Remember, we have an unknown at the beginning of the element and an unknown at the end. And if I want to find something out in between, straight line interpolation seems to make the most sense. So I start off with the equation of a line. I don't know what those unknown constants are, but I use the boundary conditions associated with this line to determine them. I know that here the displacement must be u1 and the displacement here must be u2. Based on those values, I can determine what C0 and C1 are pretty easily. It's just y equals mx plus b. This is the slope of that beam, or that bar, and this is the y-intercept, the value at x equals 0. Okay? So what I did then is I said, let's rearrange that a little bit, because what I want is a pile of junk times u1, a pile of junk times u2, and etc. And I ended up taking this mathematical y equals mx plus b and turning it into this. All right? Just a bunch of algebra. The reason why that was valuable is now if I write this in matrix notation, I have a series of functions that describe what the shape of this displaced element looked like, multiplied by those unknown displacements. So it's basically my shape functions times those constants representing the displacements. And that's why those are so powerful. Those are our shape functions. Okay? Those really are the heart of the finite element method, and you're going to see why here in a little bit. Before I do that, though, it might seem like an odd thing to go ahead and do now to try and derive a function for the strain, but I am going to go ahead and do that because we will use it here in a little bit when we actually do our finite element derivation. Okay? So I proposed to you last time that if I want to determine what is the strain in a bar, if I know its displacement, well, strain is the change in length over the original length, and if I look at a differential segment, I'm basically taking the derivative. That's what strain is, okay? So I take the derivative of the displacement with respect to x, and I can write it in that similar fashion. I have a function times those displacements, or a series of functions times those displacements. We call that the strain gradient matrix, or the B matrix. That B matrix is a very important term in finite elements because we're going to see that here in a little bit. Okay? So to summarize, because I don't want to do the same lecture twice, but just to sort of summarize where we left off, the idea is I now have these two sets of expressions that are specific to a bar element. Okay? That's one thing I really want to point out. These N functions here and these B functions here, those are for a bar element, okay? They're not for beam elements or for 2D elements or 3D elements that we're going to see later. Those are the ones for a bar. And the ones for a two-noded bar, I should point out. Because I'm going to give you all a homework where you do a more complex element, and you're going to derive it yourselves, okay? Everybody good? Okay. So now let's put it all together, okay? So I think we kind of went through this maybe somewhat quickly last time, and I'd rather take my time and go through it again because this is really important stuff. This is, in terms of the mathematical foundation, this is finite element analysis. I really think it's worthwhile to discuss. All right. So let's talk about putting it all together. All right. So we've got these two separate principles, energy principles and this idea of interpolation. Let's see what we can do to try and make some sense of it. Okay? Now, the first thing I want to do is talk about virtual work. So maybe I should go back and just sort of recap this. So again, real and virtual work, the difference being that 1/2 and what have you, shape functions and gradient functions for a bar, that was our second part. Let's take this slowly, but I really want you all to see what I'm doing and how I'm doing it. I don't want to do any magic tricks with you all when it comes to this. So when we did, let's go back to that energy principle stuff. When we did all of that discussion regarding virtual work and the energy going into the system, and it has to equal the energy coming out, what have you, we did it on a load and displacement. We did it from that perspective. The idea, here's the force, load it, what's the displacement? That's nice, but you all have had mechanics of materials, and you should know by now that if we're trying to develop a more generalized approach to discussing these types of mechanics, it's probably more appropriate that we look at things from a stress and strain perspective and not a load and displacement perspective. We can get the same response, but we should probably do it a little more generally, okay? What do I mean by that? Now, remember that, you know, if let's keep it simple. If we're talking about a bar and we're taking that bar and yanking on it, we're really only talking about one stress value. We're talking about, I guess, sigma x, you know. Take that bar, yank on it, you get a single stress, okay? Now, you all should know enough about mechanics that you don't get just one strain, because, yeah, it strains this way, but remember the Poisson effect, that if you take a member and you stretch it, it gets thinner? Remember that? So there's more than one strain, but in the end, you're only dealing with one stress. Well, my point is that in general, for any body in 3 dimensions, any, you know, physical body out there, there are 6 potential stresses and 6 potential resulting strains, right? Okay? Now, I say that I propose to you, you have 3 potential normal stresses and 3 potential shear stresses. 3 potential normal strains, 3 potential shear strains. Now, this point that I'm making right here is a little subtle, and it's actually a little different than what I was talking about before. Last time when we talked about energy, I talked about real and virtual forces. And now I've got here real and virtual strains, which is kind of like real and virtual displacements. It's a little subtle, but I think the earlier explanation, I think, makes a little more sense mentally when you're trying to understand this energy principle. I'm actually going to use virtual strains and virtual displacements for the derivation that you're going to see here in a little bit. But it might be a little subtle, but it's just something I wanted to point out. One other thing I'll also point out, you all, I know, have done analysis using a little thing called Mohr Circle, right? I know you've heard of it, and I know you've done stuff with it before. Mohr Circle is a wonderful technique if all you're dealing with is two-dimensional stresses. It's not what we're dealing with in here. Ultimately, when we do complex 3D or 3D FEA, bleh, I'm getting ahead of myself, three-dimensional finite element analysis using real applicable software, you're going to get stresses and strains in 3 dimensions. Okay? Later on, after we've gotten through some of this theory and some of this computer implementation, I want to talk a little bit about how do you actually analyze a 3-dimensional state of stress to get something from it that's useful to you as an engineer. Because it's complicated. That's not easy. I mean, if you've got some elements subjected to all sorts of stresses, how do you make some decision based off that? Like, has that element yielded? I don't know, That's tough, okay? So that takes some discussion in and of itself. And I think that's valuable to discuss, especially in this course, regardless of if you're going to be a civil engineer, or mechanical engineer, or what have you. Okay, before I continue, do you all kind of get this concept, the idea that now we're going to talk about things from a stress and strain perspective? Now, what you're going to see here in a little bit is instead of looking at things from a load and displacement perspective, we're going to look at it from a stress and strain perspective. But in order to quantify the energy in the whole system, we got to integrate. So I'm looking at a little individual element, looking at the stresses and strains inside that element, integrating accordingly. Okay? Everybody okay with that concept? Because we're going to see it here in a second. Everybody good? All right. Now, one other thing I'll point out, and I remember last time I saw that was 5.5 and it was bugging me, so I changed it. It's now 6.6. My OCD was going nuts with that one. If you have 6 potential stress values and 6 potential strain values, then just fundamental matrix algebra tells us that we can relate those with a matrix that is, just from matrix algebra perspectives, it must be at least 6 by 6, right? We call that a constitutive relationship. That's why it's called the C matrix. Okay? Now, let me say this. I have here that there's 36 potential terms in this matrix. Let me sort of simplify this a little bit so that you all have an idea of what's going on. First off, if we're dealing with a very simple material, something like steel, something that's linear, if we're assuming it to be linear and elastic in nature, a lot of these terms are 0, and a lot of them are repetitive and very simple to produce. You'll see a lot of E values, Young's modulus. You'll see Poisson's ratio. You'll see G, remember your shear modulus. You'll see a bunch of those values, but that's it. This matrix starts to get really complicated when you analyze really complicated materials. Here's a simple one. Wood is a very complicated material, or at least more complicated than something like steel. Somebody tell me, why would wood be more complicated? Say it again. Well, it's not as uniform, but there's another issue with wood. Well, wood, if we're talking about low stresses, we could treat wood as elastic. There's another issue. How about, for those you material folks, does anybody remember the word orthotropic? Does anybody remember that word? Orthotropic materials have different properties in one direction than they do in another. Wood is strongest along the grain. Across the grain, it's weak. That's why when wood splits, the grains split apart. That's because that's where it's weak, right? What about something like concrete? You all have got to know what's the issue with concrete. Concrete is a material that is very strong in compression, but it is very weak in tension. And don't get me started on like matrix composites and laminates for all of you mechanical folks. that stuff just gets real tricky real quick, okay? What gets tricky from a material perspective? This matrix right here. I'm going to be pretty fast and loose with this matrix during my derivation, but I just want you to be aware that that can get kind of tough. We're actually going to go back and talk about that matrix later when we start discussing a little bit about how materials behave and things like when do you assume plane stress conditions versus plane strain conditions, and you get different C matrix accordingly. So, but we'll get into that later. Keep in mind, we're talking about a bar right now, so that's the only thing we got to worry with really right now is just stress equals Young's modulus times strain. That's it. Make sense? Because while for any proposed body it would be a 6x6 matrix, we're only talking about an element right now that only has one stress component and one resulting strain component, or at least one resulting strain component that we care about right now. That's why all we have is that 1x1 matrix here, which is E. Make sense? All right. So last time, or I think it was the time before when we actually started talking about energy, we said, all right, if we're talking about real and virtual energy, we basically take the load times the displacement divided by 2 for real energy, but by just load times displacement for virtual energy. It's all a function of what loads you're considering, what displacements you're considering. Now, I have here a proposed model that I say defines what the strain energy is as a function of stress and strain. So what's different? Okay, I've still got that same concept that if I'm talking about real energy, I've got the 1/2, and virtual energy, the 1/2's gone, right? I've still got that. I've still got the idea of the difference between real quantities and virtual quantities, that little delta corresponding to a virtual quantity. What's different? Here I'm talking about stresses and strains. Before, it was just the load times the displacement. Well, now what I'm saying is it's the stress times the strain, but that's infinitesimal. I've got to integrate over the volume. So that's what I've got here. This definition is no different than what we had before. No different. It's just expressed a little more with a little more finesse, I guess I could say. Is that all right? Okay. Now, I swapped the matrix multiplication and put a transpose there. Does anybody remember why? Does anybody remember why I've got this transpose here? Because I can't take a 6x1 column and multiply it by a 6x1 column. Matrix math doesn't work like that. But if I take this and transpose it, then a 1/6 times a 6x1 will actually give me a value I can integrate. Okay? Everybody all right with that? Okay. Now, keeping that in mind, this whole concept of energy, okay, keep that in the back of your head. I might write it up here on the board, although I'm going to use the whiteboard on the screen here in a second. So I'll say my virtual energy, because that's the only one I'm really going to care about, is the integral over the volume of delta epsilon transpose times sigma, and that integrated. I'm going to use the board here in a second, so I want you to see where this is coming from. Everybody all right? Now, let's go back to this. We defined functions for displacements and for strains, and we said that they were the column of constant, those constant displacements at the joints, so the U1, U2, whatever, times either an N matrix if we're looking at displacements or a B matrix if we're looking at strains. We came up with those terms accordingly. Everybody all right with that? Okay. So what I propose to you is all we see here is I'm looking at that, that difference between, well, what if I'm dealing with real values or real quantities versus virtual quantities? Everybody okay with that? Okay. So, this is a subtle note regarding matrix math. If you have A times B and you want to take the transpose of the whole thing, you can take the transpose of each individual term, but because of matrix multiplication, you have to actually swap them. You can prove that actually pretty easily. But my point is that if I've got this virtual displacement equals N times this, if I take the transpose of that, I got to swap them. Everybody okay with that? Okay. So see what's happening here. I know that there's a lot going on this slide. This is actually a pretty critical slide to see where stuff's going on. So this term right here, the delta epsilon transpose, that becomes, I mean, that's strain, right? So it's B times your displacements. We're talking about virtual displacements and their transpose. Does everybody see how we're getting this right here? Everybody see that? So this term is becoming delta D transpose times B transpose. What about this term right here? That's real stress, right? Real stress equals our constitutive matrix times real strain. What's real strain? B times D. So this term right here becomes C, B, D. So see that? Does everybody see how I got that? So I know that going from here to here, there's a lot of substitution, but it is pretty straightforward, right? Everybody good? All right. Now, okay, that's our internal energy inside the element. Everybody good? What about external work done? We split that up into three categories: body forces, surface tractions, and point loads. Okay? Here, I think it's easier to kind of describe the physical meaning. For instance, let's take this computer. It's a very odd geometry. It's got really odd support conditions. In the end, though, this computer is subjected to body forces right now. What's a body force it's being subjected to? What forces are being subjected to right now? It's self-weight. And its self-weight is essentially acceleration acting over its mass. That's where we get that weight component. All right? And it's being applied over its volume. That's where that unit weight, that density concept comes into play. That load is distributed over its volume, right? That's where a body force comes from. A surface traction, I'm sorry, I'm a civil engineer. The easiest way I can describe a surface traction is if we're looking at a pile foundation. Pile foundations get their resistance from the tip capacity, but also, and more critically, from skin friction. That force applied along the pile, okay? You take a pile and you drive it into the ground, that pile is resisted by the friction of the ground. That's where you get your capacity. And any civil engineer should know that. I'm sorry for the mechanicals. That's the example that comes into my mind. But I'm sure there's all sorts of friction stuff with mechanical engineers, right? Don't y'all take a class like in that, like is it like tribology or something? That's what that is the study of friction and how it works. So, okay, and point loads, that's just the energy you get if you have a load applied directly to a joint. So we can calculate, or maybe I should say we can derive expressions for external work done from a real standpoint and a virtual standpoint. And here you can see it's all fairly straightforward. It's just a function of virtual displacements, forces, and what have you. Everybody good? Now, if we go through and do that same substitution, looking at those virtual displacements, that's where we get this, okay? Everybody good? Now, the nice thing about this is that if we set the two terms equal to one another, the real or the virtual internal energy and the virtual external work done, we get this expression. Now, I really want to take some time and digest what's going on here, okay? Does everybody understand how I got to this slide? If you've got any questions, please, this is the time to ask. Everybody good? Okay. All right. Notice how every single one of these terms has a delta D transpose, right? That corresponds to an arbitrary, fictitious set of displacements. And in the end, those displacements are constant values. It's a D vector. So I propose that, let's put it like this. If I have, a pile of junk times 2 equals another pile of junk times 2, does the 2 really matter? No, I can just divide that out, right? Every term has a delta D transpose. I'm getting rid of it, okay? Bam, they're gone. Now, what do I have? This equation in this box, I almost want to put stars all over it. It's one of the most fundamental equations in this whole class. What do I have here? I have a pile of junk times D equals this. Stiffness times displacements equals loads. I propose to you that to calculate your stiffness matrix, this is your stiffness matrix, this is your load vector. This slide is probably the foundation of everything that we do from here on out in finite element land. Promise. Now, some of you are probably like, this really doesn't look like a stiffness matrix, Dr. Michelson. It will, really shortly. Everybody good? Okay. Now, this is just so you don't think I'm completely pulling the wool over your eyes. If I do a volume integral, how does that work? Let's remember, you all took calculus, right? A volume integral. I take a little individual element, I evaluate that function over that element, and I do that across the whole volume. I'm summing. That's what an integral is, a Riemann sum across the whole whole domain. Well, if I have a constant area across that domain, or at least that function is constant across that domain, I can say, well, look at this. If this function is constant across a certain domain, I can factor that out, right? Isn't that how integrals work? If I have a constant in there, I can factor it out, right? Well, if I assume that my function, let's say my stress is, or whatever, is constant over the area, which is common in a bar, right? The stress is constant over the area. I can factor that out. What's this double integral of dA? It's just the area, right? So I propose to you that instead of doing a triple integral over the volume, I can just pull an area on the outside and just integrate over the length. Everybody okay with that? All right. If you're okay with that, watch this. All right. You're going to like this. Let's look at this for a little bit. Finite element derivation of a bar element. So, first off, let's look at the mechanics. Now, any time that we're looking at a mechanics-based problem, in general, we're looking at the stress equals some constitutive relationship, I can do better than that, times the strain. But we're looking at a bar. Just take a bar, yank on it, right? So because of that, I'll say for a bar, all we care about is one stress value being Young's modulus times the strain. Everybody okay with that? So I propose to you that my C matrix is just going to be a value. It's just going to, here, maybe I should put my brackets here so that we're clear on this. My C matrix is just some number E. That is for this problem. Okay? Now, let's see. N and B matrices. For this, I really only care about the B matrix, so maybe I should just keep this simple and just say, how about just the B matrix? Anybody remember what that is? Minus 1 over L and 1 over L, right? Everybody okay? So if I want, I could say that B1 is minus 1 over L and B2 is 1 over L. Everybody okay with that? Now, what about our domain? Forgot the I. Let's see, what time is it? How am I doing on time? I'm doing pretty good. Good. Domain. Here's my bar, right? Right? And I have some node here. Remember when we did our calculation or our derivation of our shape functions, we said that this is where x equals 0, right? And we said that this is where x equals what? L, right? So my point is when we do our integration, we're going to integrate from x equals 0 to x equals L. Okay, now watch this. K matrix. I propose to you that the K matrix is defined as the triple integral over the volume of B transpose CB. Oh, goodness. Integrated over the volume. Okay? Now, let's just sort of take this step by step. I'm proposing to you that for a bar, for a simplified bar element, that the stress and the strain are constant along the area. And since I can factor that out, I'm saying I can simplify this by saying the area times the integral over the length of B transpose CB, and I'll say D length, just to keep it simple. Everybody all right with that? Now, let's do a couple things right here. What is C? Is that a matrix or is it just a value? It's E, right? Is E a constant? It's just a number, right? What can I do with numbers? Pull them out, right? Okay? So I propose to you that we can say that this is AE times the integral of, now watch this, x equals 0 to x equals L of B transpose times B dx. Everybody all right with that? Watch this. What is B transpose? It's that, right? Okay? B is that, right? So I need to integrate that by dx. Is everybody okay with that? Now, this has become a problem that you all should be able to do, and you should have been able to do since Calc 1. Look at this integral and pay attention to it for a second. Is this the integral of a bunch of variables or a bunch of constants? What am I integrating with respect to? X. Is there any x's in here? So can I just pull all this stuff out? Right? Okay. So I propose to you that we can do this. Here, I'm going to be verbose with this because I want to take my time with it. Oh, nope. Everybody all right with that? All right. We're going to take the complicated parts of these one at a time. I'm going to look at these matrix multiplications and this integral one at a time. Let's start off with the simple one, the integral. We have the integral from x equals 0 to x equals L of dx. What is the integral of dx? X. So this is x evaluated from x equals 0 to x equals L. The fundamental theorem of calculus states I plug in the top number, get a value, plug in the bottom number, subtract it, right? So that's Is that a fair statement? Okay. So Could I then rewrite this as AE times L times minus 1L, 1L, minus 1L, 1L. Is that a fair statement? Okay, now, let's handle those matrices. Remember my trick I showed you that if you've got two matrices, you take the left one, put it on the left, the right one, put it up top, right? Y'all remember that? So let's do that over here. So I'll sort of do that over here. So the left one, the right one, put that here, right? So my answer for this matrix multiplication is going to go right there, right? It's going to be 2 by 2, right? Is everybody all right with that? So let's take this one step at a time. Let's talk about this term right here. How do I get that? This times that. So what's that term in the top right-hand corner going to be? Or top left-hand corner? 1 over L squared. What about the one in the top right corner? Minus 1 over L squared. Minus 1 over L squared, 1 over L squared. Does everybody see that? So this term right here, it equals what? AEL times what? 1 over L squared minus 1 over L squared minus 1 over L squared, 1 over L squared. Distribute that out, and I get I don't have a microphone, so mic drop. Can't get any laughs out of you all. Goodness. Did everybody see what I did? Okay. The point that I'm trying to make with this is that we can take this simple element and apply this procedure to get a stiffness matrix. We can apply the same procedure to get stiffness matrices for much more complicated elements. But do you see how this works? The point is, let me go back to my slideshow. Okay. And I'm going to walk through this. I know you all had these slides, but I think there's something to be said about actually going through and actually doing the math and then sort of going back and reviewing. This is the stiffness matrix for a bar element. I propose to you that you could get the same thing here. Okay? So if you have B and B transpose, you can calculate B transpose times B to get that. B transpose times C times B will give you that. I'm just doing the same derivation, maybe doing it a little differently, but it doesn't really matter. But my point is that everything inside this B transpose CB is a constant. Because of that, I can factor everything out. The integral of dx is x evaluated from 0 to L gives us this. Okay? You all have any questions? You all have any questions? All right. This is what I'm going to do, and I want you to be prepared for this. Next time, we are going to do a derivation start to finish of a beam element. Okay? It's not in the slideshow. I do that for a reason. You all need to go through the process by hand and grunt it out to really understand what's going on with this. Okay? Come with notebook paper, come with whatever. We're going to do it together. Okay? I'm trying to think if there's anything else worth mentioning. One other point I'll mention, we actually didn't do a lot of discussion with the bar element about this, about our load vector. The reason why is for bars, or at least the bars that we've done so far, we really don't consider body forces and surface tractions, so we just write our load vector. It's pretty simple. We're actually going to go through this. Y'all remember those whole, let's see, Remember these, the fixed-in force vectors that I just gave you? Remember those, like the table, the QL squared over 12 and all that? We're going to use this methodology to derive those as well, okay? So I really want you to be aware of where this stuff is coming from, and I think the only way to really understand it is to just do it. So next time we're going to do a beam element start to finish. Be prepared for that. There's going to be a lot of calculus, going to be a lot of alphabet soup, a lot of symbols going around all over the place. Be ready for it. Everybody good? That's all I got. I will see you all next time. Remember, you got a homework due Thursday, and you all have your take home. That's all I got.